We have a soap bubble of radius r that is inflated. So how can we inflate a bubble, an already existing bubble, without adding extra gas inside it? So the hint of that is given in the problem itself, in the question. That is, we need to find the molar heat capacity of the gas during its heating inside the bubble. So now you can imagine that if you have a bubble and you heat the gas inside it somehow, then the bubble is going to expand. So when the radius is r, which is given to us, at that instance, if you heat the gas, what will be the molar heat capacity? That's what we need to find. So because this problem is concerns with the gas that is inside, let's take our system, which is the gas itself. So inside this shaded part, inside this dotted part, we have the gas, and when the gas expands, we are still considering the gas alone. So our system comprises only of the gas. So we are not bothered about the atmospheric pressure and the work done. So work done because of the work done on the film, and we are not bothered about work done by the atmosphere anymore by limiting our system. So let's read what we just discussed. So let's say the radius of the bubble increases by dr when temperature increases by dt. And we are considering gas as the system, so therefore we don't need to bother with work done by atmosphere or energy stored in the film anymore. Unlike the previous problem. So in previous problem, we were taking some external gas and we were putting that gas inside to increase the bubble size. So that was problem 2.181. So in that case, we had to bother with the work done in the compression of the gas and work done on the film formation. But here we are heating the gas from the inside. So by limiting our system, we don't need to bother by the atmosphere and film anymore. And what is the process of the gas? So that we'll figure out by starting by our general equation, dq is equal to du plus pdv. So whenever we need to find molar heat capacity of any process, either known to us or unknown to us, we start with this equation. That is the general energy equation for the gas. Because our system is the gas, we can write this equation. So dq will be n naught c dt, du will be n naught cv dt, and this will be just pdv. So this becomes c is equal to cv plus pdv by n naught dt. Now p, pressure, volume, temperature, nothing is given to us. Only thing given to us is r. So now, but you can imagine, you can write pressure in terms of r, right, inside a bubble. You can write dv in terms of r, that will be 4 pi r square dr. And you have a term of dt. So let be there, but let's write the other terms first, what we already can write. So this becomes cv plus p becomes p naught plus 4s by r, and dv becomes 4 pi r square dr. And at the denominator we have n naught dt. So we have a term of dr by dt now. So how do we get that relation? So that we can get by writing our gas equation, because that is the only way we can introduce temperature. And again, pressure and volume we can write in terms of r. And then if we differentiate both sides, we'll get a term of dr by dt. So let's do that. Pressure will be P naught plus 4s by r. Volume will be 4 by 3 pi r cube is equal to n naught RT. So we do dr by dt, and I've skipped a few steps here on differentiation, but it's in maths, you can do that. So if you take r cube inside, this will be P naught r cube plus 4s r square. And when you differentiate that with respect to r, so you'll get the term of dr by dt that comes to be this. So I've got dr by dt now in terms of small r, and that's what we needed because everything else is already in terms of small r. So we put that value there and we get our answer. So this is the molar heat capacity. When the radius is r, so obviously it changes with small r. And from this equation you can also see when r is large, then molar heat capacity is less. That means as the bubble increases, less heat is needed per mole to increase the temperature of the gas. So when the bubble is small, the change the heat needed to raise the temperature is more. Once it is larger, heat needed is less. So this is the molar heat capacity. And the problem is asking C minus Cp, so you can just subtract Cp from this and get your answer. But this is the more general term, which is just molar heat capacity. All right.